So today let's continue with the spectral element method, and the theory part that I want to come into is how we construct the matrix form for the spectral element method. For that, we're going to look at how now the expressions look like for mass matrix or the capacity matrix and the stiffness matrix and the force term. So we're going actually to write out this in detail to see how these contributions will look like. And then basically, yes, just as usual, have the assembly part and the time scheme then as well. So for the matrix form, let me start with first recalling what the equation is that we look at. And for that, I share the iPad here. Let's hope it works this time. Right. So you should see the whiteboard, no?
We are seeing it.
Good. So this summarizes the first part of the spectral element method that we looked into. And the first part is basically the very first step in the spectral element method. So we take the heat equation as example, and then write the weak form or the variational statement of the equation in the first step. And so I wrote this down already. So for the weak form, for the heat equation, that becomes this mass term or capacity term on the left-hand side. And on the right-hand side, we have the stiffness term and the boundary term. So that is clear so far? Good. So what we want to come to is the matrix form. So let me write this down now. So we are interested in the local contributions to these mass matrices, stiffness matrices, and also the boundary terms. And in order to obtain the matrix form, we have to start with the expansion of our functions. So what are the functions in this example? We have W, this is the test function, and we have temperature T. So let's look at the expansion of these functions. So we expand our function in the following way. We have W of x, and x is a function of xi, the local local element coordinate. And we're going to expand it on our basis function. So do you still remember what the basis functions are in the spectral element method? Go and look up your notes.
Are we talking about the Lagrange shape functions?
We're talking about the basis functions, but they are also Lagrange polynomials.
So it's not the 1/2, 1 minus
no
epsilon? No.
that's the shape functions. The shape functions are used for the mapping from the physical domain to the reference domain, or from a physical distorted element somewhere in space to our reference element, which goes from -1 to 1. That would be the mapping, the shape functions for the mapping. Here we talk about the expansion of the functions. That's the basis for the function expansion. It's also Lagrange polynomials, but high order Lagrange polynomials.
Alpha. F alpha, L alpha, L n alpha, set.
Right. So here, let's start with these beta indexes. Goes from 0 to n, the order of the Lagrange polynomials. And then we have a coefficient W beta times now the Lagrange polynomial of order n at position psi. So this would be the function expansion for the test function W. So LB, this is the high order. And the degree of the polynomial is degree n. So Lagrange polynomial. These Lagrange polynomials can be degree 4, 5, 8, 12, 16, etc. So it's higher order usually. And then W, this is just the expansion coefficient. So the same for the temperature field. We use the same basis functions, so meaning the same Lagrange polynomial here. Let's use an index alpha to n. Then the coefficient will be T alpha. And these coefficients depend on time. Since if you want the temperature field, depends on time t as well. And then times the Lagrange polynomials. Here we can write L alpha of psi. Should be L for Lagrange. Yeah. So who remembers how we call this approach? You see, we use the same polynomials, the same basis functions for the test function, but also for our like field that we are interested in this case, temperature, right? So when we use the same basis functions for both, it's called the Galerkin's approach. So that's Galerkin's method that we also use here. So we have the expansion, and then a little note to that one with the test functions. So you saw it for the finite element as well. Here we can choose what these W beta coefficients are, because the test function is an arbitrary test function. So we can choose what the coefficients, for example, should be. And in order to construct now the matrix form, we will again use basically just one coefficient to be 1 and all the others to be 0. So let's put this. Do you have a question?
If we say the Galerkin's approach, the L beta and L alpha is the same, so does it mean that we have the same GL points, right?
Right. Yes.
The same points, the same shape of the functions.
Yes. So in principle, Galerkin's approach or Galerkin's method means that the basis functions, they span a function space. So all the functions that you can build with this sort of basis, for example. So we use these high Lagrange polynomials as basis functions. So they build a function space, and the function space is the same for the test function and for the solution, like temperature field or displacement field. And so when this function space is the same for both, that's called the Galerkin's approach.
Okay, okay.
So here it also means, yes, they use then the same GLL points, but you see the GLL points are used for the quadrature. When we want to evaluate then what the integral values are, we use those GLL points together with these polynomials. Here for the function expansion, just think of having polynomials into which you expand your function. But yes, the polynomials will be very specific and using basically the GLL points as roots. So they, in this case, they go together. Yes. And they will be the same for both test function and the temperature field in this case. So let me quickly put down that note about choosing. We can choose the test function. Or if you want the test function coefficients, which in this case would be these W beta coefficients. We can choose them so that, for example, that they are all equal to 0 except 1. Which we will set to 1, the coefficient. What does it mean? Basically, it means such that we can treat each of the Lagrange polynomials one at a time. So if, let's say, W beta is only 1 for beta equals to 2, then only the Lagrange polynomial L2n will actually contribute. And it also means at which point is L2n, the polynomial, non-zero? So think of that little figure that we made, for example, for degree 4, we have these 5 points. You have something like this, for example. This would be psi, let's say psi beta. equals to psi. So we start with psi 0, psi 1, psi 2, psi 3, and psi 4. Now L2, 4 is only 1 at psi 2. So see L2, 4 at psi 2 is 1 and 0 on all the other locations. So if we set W beta, so if we have W2 equals to 1 and everything else to 0, then only this L2 polynomial will contribute. And the L2 polynomial is only 1 on the GLL point psi 2. And everywhere else it is 0. So it means that once we set the coefficient for W, we basically look at the solution for just one particular GLL point. That's the only non-zero contribution that we will have. So here this basically means we are considering one GLL point at a time. Does that make sense?
So in this way, W will equal to 1 only, right?
W2 is equal to 1, yes. So we only set one coefficient to 1 and all the others will be 0.
Yeah, I mean the final result of W is only 1.
Oh, of the test function itself, you mean?
Yes,
You-
yes.
The test function, yes, it will be the test function, if you want, W of x of psi will only be 1 for position psi 2. Is 0 except at position psi 2 at that GLL point where it would be 1.
What did you mean with one at a time? I mean, it doesn't depend on time. It's always one, right? It's always the same.
Right, but we can now just change the coefficients. So we repeat this choice of the test function as many times as we have GLL points. So we keep changing the test function. And every time when we choose a new test function, we just select one of these W coefficients to be 1 and all the others 0.
And how do you do that? Randomly, or depends on some geophysical, physical?
No, in principle, to set up our linear system of equations, we will have as many equations as we have points, GLL points, and unknowns. Then we can determine the unknowns. So for each GLL point in our mesh, if we choose the test function such that only the coefficient for that GLL point is non-zero, is 1, then everything that falls out from the weak form is an equation for that degree of freedom on that GLL point. And then we choose the next test function such that it is only one at the other GLL point, etc. We keep doing that. Because then we can set up this system of equations. Okay, so let's do that. Maybe it also becomes then clear when we write this down. So we do this for the terms here that we have: the mass term or mass matrix, the stiffness matrix, and then the boundaries if you want. But so let's put this function expansion into the mass matrix, for example. So let's focus on the mass matrix. So what we look at is the left-hand side term, which looks like this. Is the integral from 0 to L over W rho C time derivative of t in dx. And you saw once we discretize this into finite elements, this is going to be the sum over all these element integrals that we have of this guy here. So let's look at the contribution from one element. So what we have is then contribution from element omega E. Looks like this. We have the integral rho C times the derivative of t. And so this we're going to map onto the reference element, which goes from -1 to +1. Then we have rho, now x becomes a function of xi, the local coordinate, c the same. We have w x of xi, and then the time derivative of the temperature field times the Jacobian times d xi now. Oops, a bit ugly. So the Jacobian deals with the mapping to the reference element, and now we integrate over xi rather than x. So you see we have now the function expansions here for the test function and for the temperature. So let's do that. So we're going to use the quadrature to evaluate this integral. So it's an approximation of the integral value. And if you look at the quadrature formula, it uses these weights omega, this omega hat, and integrates over our GLL points, where we use now gamma as the running index. Then we have rho, the coefficient on the GLL point gamma. The same for the specific heat. And the same for the Jacobian. And now comes our function expansion for W. So here we have beta 0 to n. Then we have w beta times our Lagrange polynomials. And so this will be evaluated at the GLL point gamma, which is psi gamma location. And then we have the function expansion for the temperature, where we have time derivative of the temperature coefficients T alpha times the Lagrange polynomial alpha evaluated as well at psi gamma. So this part is clear. So omega hat are the integration weights from the GLL from the integration rule or the quadrature rule. W beta are the coefficients for our test function. T alpha are the coefficients for the temperature field, and they depend on time. So we take the time derivative onto these coefficients. Good, and now look at these evaluations of the Lagrange polynomials. So the Lagrange polynomials for the quadrature rule are evaluated at the GLL point psi gamma. And so if you look back into the part 1, the thing we looked at last time, you will see that these things here they become these Kronecker delta functions. We have delta beta gamma, and here we have delta alpha gamma. Which is a way of writing that the Lagrange polynomial is only one on one particular GLL point and 0 everywhere else. So only if beta is equal to gamma, then the Lagrange polynomial is 1. If beta is different to gamma, then the Lagrange polynomial value will be 0. And all the other GLL points. And so for alpha and gamma. So this simplifies now quite a bit. So this sum over the gamma GLL points we still have that one. Now this sum over beta, what does happen to that one? In principle, we have to set beta equals to gamma. Only that term is actually non-zero. So what happens to this test function is that we have then W gamma and the Lagrange polynomial at psi gamma will be 1. And the second summation over alpha, exactly the same thing. Only if alpha is equal to gamma, then we have this non-zero term times L gamma at n at psi gamma, which is equal to 1. So we don't need to write these times 1. So you see, because of that property of the Lagrange polynomials, that they only are 1 at the one particular TLL point and 0 on all the other TLL points, these sums basically just simplify. And the only sum that we have is this sum over gamma, which comes from the integration rule. And so if you think of a matrix form, then we will see that later on. But the matrix form, when we construct it, this one becomes now diagonal because we only have the value at gamma, which is non-zero. Everywhere else on all the other GLL points, it's 0. So that makes it that we have this diagonal form of the mass matrix or the capacity matrix, if you want. So this is a big, yeah?
Can you say it again? Why this is a diagonal matrix?
We're going to see it, but in principle, what we are after is the mass matrix, which is a matrix Mij with I and j. They go from 1 to n, and n being the number of GLL points. And so Mij now is only 1 for I and j equal to each other, and 0 if I and is not equals to j. And Mii, we just write it as Mi. Or if you want, I being M gamma, the GLL point associated to that gamma index. We come to the matrix form afterward. Hopefully it becomes clearer as well to see how that will look like. Good. Let's put this somewhere for later. So right now we have the mass matrix contribution. That's for each element that we're going to map into a reference element. Now this, what we wrote down, is the local contribution from that element. So keep that in mind. This is the local contribution in element gamma E. So what we do now is basically do the same thing for the stiffness matrix. See, we come here. Let's look at the next term, the stiffness term. for this one, let's just make it very short. So for the contribution from element omega e, the term looks like that. We have the integral over omega e of kappa, the conductivity times these derivatives with respect to x times dx. Probably need more space on the other side, which we're going to evaluate in the reference element. It goes from -1 to +1. So now the conductivity is position of x, which becomes a position of xi, our local coordinate. And now we have the derivatives of w, x of xi, and the derivative of the temperature field, which depends on position and time. And now at times j, sorry, forgot that one, because we need the mapping. So the Jacobian times now the integration variable dxi. So in this one, we're going to approximate by the quadrature. So now it becomes the sum over our GLL points, gamma. So we have the integration weight times the conductivity coefficient at that GLL point, gamma. Now we have to write down what the, well, let's take the Jacobian as well here. So we have the Jacobian, J gamma, and now the function expansions. So we have our sum over beta of the test function. And you see that derivatives with respect to space become the derivatives of the Lagrange polynomial. So we have these L prime polynomials, L prime n at position psi gamma, and the additional derivative of psi with respect to x evaluated at psi gamma. So this is going to be the derivative with respect to x when we do the derivative in the local coordinate. So here you see we have L prime, that's the derivative of the polynomial with respect to psi, times these derivatives of psi with respect to x. So this is psi over x evaluated at position psi gamma. Then we have taken this, the derivative of the test function with respect to x. Is that clear? Good. And you see the same we have with the temperature field here. So for the temperature, we had alpha index. Use these alpha indices. Then we have the coefficient T alpha. And now again, the derivative of the Lagrange polynomial of prime alpha, degree n, evaluated xi gamma, times again this derivative term, which is xi with respect to x, evaluated at xi gamma.
Professor, why is it with respect to x? Because, oh, okay, I see that.
It comes from this part here. So we're going to do the derivative now in the local coordinate xi. So in order to do that, we have to take the derivative of the polynomial times this additional xi with respect to x. Okay. So, yeah. Here the little note is basically what is the derivative of like a polynomial, like L alpha with respect to x. It's going to be the derivative of L alpha with respect to xi times xi with respect to x. The chain rule basically. So what is L, the derivative of a Lagrange polynomial evaluated at a GLL point xi gamma? You see here on top with the mass matrix, we had not the derivatives, but the polynomials. L beta xi gamma was this delta beta gamma function. Now we have the derivative of the polynomial evaluated at xi gamma. Is that still the delta function or not? Let's look, for example, at this little figure with one of the polynomials. What do you think about the derivative of the polynomial evaluated on the GLL point?
Zero?
So maybe in this one, here the derivative looks something like that. Maybe this one, this one. So you see the derivative of the polynomial is certainly not zero on, let's say, xi3 or xi4 anymore. the derivative of these positions is not zero. So that property doesn't hold anymore. So here, this part, the derivative of the polynomials evaluated at the GLL points is not zero anymore. Which means we have to keep these additional summations now. It doesn't simplify further. The only way we can simplify it by choosing here this W beta coefficients. We say we only set 1 to 1 and all the others to 0. Then only this first part will simplify. But we still have here, for example, the sum over alpha, which we have to keep because the derivatives are non-zero at the GLL point locations. So,
So Professor,
yeah,
the derivative is zero just in the case that gamma equals beta, right? If not equal, then it's not zero.
For this particular polynomial that I just draw you, that's right. But choose another polynomial, for example, choose L0 for, which would be a polynomial that, oops, looks like that. So we take our 5 GLL points and L0 for would look something like that. Is 1 at xi0 and 0 on all the other points. So this will be L0 for xi. But so here the derivative on this particular point is certainly non-zero as well. And so it's non-zero on all the other GLL points. So in general, we cannot say it's zero at the particular point or not. We do have to evaluate it. But what we can do is play with these W beta coefficients of the test function. So let's do that now. So let's choose as a test function something there where we have W at a particular GLL point, let's say beta 1 is 1 and all the others are 0 for all GLL points beta which are not equal to beta 1. So what do we find? So we have the mass matrix is going to be, look at the local contribution of the mass matrix. So gamma is only 1 for beta 1. So the only non-zero term is this omega beta 1 contribution, rho at beta 1, c beta 1, the Jacobian, and then our test function coefficient beta 1, and the time derivative of the temperature coefficient at the GLI point. This is from the mass matrix term on the left-hand side. On the right-hand side, now we have to keep these summations. So we have the capacity, Jacobian, and now the test function polynomial. We have the polynomial L beta 1 and evaluated at gamma times this derivative at gamma. So here the summation simplifies for the test function. The only non-zero term will be the one at beta 1 times, well, this should be in the same line, but times now the sum over alpha of the temperature coefficients, T alpha, and the Lagrange polynomial alpha evaluated at the position psi gamma times x of psi at psi gamma.
Professor, in the capacity matrix term, you should not have W beta 1, right? It's 1.
This one, yes, it's just 1. So we don't write it on the right-hand side, you're right. Here we would have this W1 coefficient as well, but since this one is 1, we didn't write it down. Right. So what we can write down is in this form where we have m beta 1, and then we only want to have the coefficients. The temperature field, oops.
Professor, where is the boundary terms?
Oh, we don't, just let's ignore the boundary terms for now at the moment.
Okay.
You're right. We still have to deal with those then as well. But this is just to give you an idea about the main structure then of the matrix form. So we can write this as a mass term m beta 1 is equal to the sum over alpha n k beta 1 alpha times the coefficient T alpha. So here everything in this part is becoming m beta 1. And on the right-hand side, we're going to rearrange the terms. We're going to rearrange the summation a bit, that we can write everything in terms of a T alpha coefficient. And so if you think of the, let's just get rid of this part. Of a matrix form, what we could write here is a matrix M times a vector, the time derivative of the T vector, the coefficient vector for T, equal to be a stiffness matrix times the T vector again. So take a moment at home to try and recognize this, that we can actually write it in this matrix form. So think of these coefficients as being this part here for GLL point beta 1, and then the contribution for the stiffness matrix, for example, the element beta 1 alpha would have this summation of the gamma times the Jacobian times the derivative of the polynomial beta xi gamma times the polynomial alpha at xi gamma times these mapping terms xi with respect to x at xi gamma squared. So this would be a single element entry in the stiffness matrix.
I think it's missing an N here.
Right here, this one.
Yeah, thanks.
Good, yes. Yeah, it looks a bit funny with this prime n, but the prime should denote the derivative of the polynomial L prime. And n is the degree of the polynomial. So if you want, we could also leave out the degree n. At some point we just could simplify the notation a bit.
And we are still in one element, right? Just one element.
Yes, right. So these are local contributions. Yes, for element gamma E, these are the local contributions for the mass term, mass matrix, and for the stiffness term. And then comes the assembly part, basically, which then assembles all these local contributions into a global. So last note here. Notice that mass and stiffness matrices are constructed at the reference or the element level. So the reference element level which allows for material heterogeneities within an element. So you see density, capacity, conductivity. They're specified at the element level. So what about the boundary? Let's finish with the boundaries and then call it a day for today. Boundary conditions. So in 1D, then these conditions can be written as, let's say, at the boundary x equal to L. Then we have this term W kappa, the derivative of T, which would be the test function coefficient at n, assuming that n is the GLL point at the boundary L times capacity, and now we have to keep for the derivative these summations. Here we can use alpha to n T alpha times alpha, the derivative of the polynomial alpha, n evaluated at that GLL point at xi n times this mapping term xi n. You see what this contribution looks like? So we evaluate at this very last GLL point, where we assume the index is n for that GLL point. So we are somewhere in this last element and look at the local contribution. And here the positions go from xi 0 to xi n, the GLL position. And so if we are at the very end, the last GLL point, this will be the position xi n. But then again, because the polynomials, the derivative of the polynomial is non-zero on all the GLL points within that element, we still have to keep that summation. And so the same for the boundary on the left side would be this term, the boundary term evaluated at the last position or at the very first position. Here we can say, well, this is position 0. So the coefficient of the test function times the conductivity. And again, now this sum term where we evaluate the polynomial derivatives at this time at this position psi 0 GLL point plus the mapping derivative. Oops. Evaluated at psi 0. So for the derivatives, there will always be a non-zero contribution from all GLL points. So what we are interested in is the value at one particular point, but this will have non-zero contributions from these derivatives of the Lagrange polynomial. So we sum over all these points within the element and add these non-zero contributions from the derivatives to evaluate then the actual value at that particular GLL point. Good. I would say let's stop here. We are already at the end of today's class time. So I would say try and think at home again about this matrix form. Try to make clear that we can write it in this matrix form. But so all we did is basically we started with the function expansions. And then could write down what these local contributions are for mass and stiffness matrix. And then finally write down what the matrix form looks like. And then again, yes, here we would have the boundary term, which we just mentioned now at the very end. So only on these very last and first element, on these particular points, where we have actually these contributions. Do you have a question for that? I would say let's plan for next Sunday to start with the example where we implement and then the spectral element method for the heat equation. We go through the heat equation example, then we'll also look into how we do the time stepping. But there will be no new addition, basically. You saw it from the finite element example, how to do the time stepping. We can just do the same thing here. Really, the variation from the spectral element method comes into this part here with the mass matrix and the stiffness matrix. And then, yes, let's use next Sunday for the homework example for this spectral element method. Then we can also look at the homework from homework 6 from the finite element method, because they're very close to each other. Is it good with you? Good? Everything clear about this part?
Professor, so we will discuss a little bit about the homework 6 next time?
Yes, let's do it on Sunday, yes.
Okay, okay.
Because you should see then as well how close then basically the implementations are. between the finite element and now this variation with the spectral element.
Yeah, because actually I have some puzzles about homework 6. So
I'll
maybe
put the solution into the Dropbox. If you want, look at the solution as well to figure out if your implementation looks similar to that one. And then I would say, let's discuss it next time. Yes, let's discuss it on Sunday.
Okay.
Good. Then we're all done for today. And I wish you, for us, it's already weekend time. If you want, just start your weekend as well.
Thank you, Professor.
Good.
Thank you, Professor.
Thank
Thank you,
you.
Professor.
Have a
Thank
good
you.
Good.
weekend.
Enjoy your day.
Bye.
Bye.